talk, it's my pleasure to introduce you Rose Elliott Smith from University of Chicago, who will speak about uniformly expanding random walks on manifolds.
Hello, thank you for having me. Holler in the back if I'm talking too loudly into the microphone. All right, so I will be talking about uniformly expanding random walks. Also, a heads up that this talk is just 30 minutes, so if I'm light on details, forgive me and quiz me later. All right, so to start out with, the general structure of what we're going to do. So we'll start out talking notation, and then obviously I need to define this concept for you and motivate why you should care at all. And then we'll talk about the work that I've done on this, and if we have time, get through some of the strategy of the proof. All right, so notation. So for the remainder of this talk, M is a closed D-dimensional Riemannian manifold. G will be volume preserving diffeomorphisms. You can consider all of this setup in the non-volume preserving case, but it tends to be slightly less interesting because a lot of the more complicated problems come from restricting to volume preserving case in particular. So mu is a probability measure on G. This will be the law of our random walk. Nu is a mu stationary probability measure. So in the random walk setting, just as a very brief reminder, to say that we have something that's invariant is a very strong property. Invariant measures are not guaranteed for random walks. So instead, we usually consider mu stationary measures. And in this case, I will usually denote them as nu. The mu stationary measures could be on M or on the tangent space or on the Grassmannian. I will abuse notation for all of those spaces with the same measure. And then just the last bit of notation is that GR will denote the kth Grassmannian bundle. In general, what we're interested in here is the growth of subspaces and vectors. So very often as we go through, we'll be interested in questions of how does the kth subspace grow? How does the k-1 subspace grow? So if you're not familiar with Grassmannians, you're welcome to just replace this with tangent bundle, and most of the ideas will go through quite the same. Yes, and then just in case people are unfamiliar, a mu stationary measure means it's invariant on average. So it's invariant under the convolution by mu. All right, so what is uniformly expanding? Uniform expansion says that there is a step of my random walk after which every vector has grown on average under my random walk. So a key thing to notice here is that this is for every x and every v. This is not a property that holds almost everywhere, as is more often what we ask for. This has to hold at every point. So when you first see this, it looks like it's quite a strong thing to ask for. I have to have expansion at every point. The saving grace here is that randomness is much easier than the deterministic systems. So asking for growth at every point is easier if I ask for it for almost all futures. And this turns out to be not as strict of a condition as it initially looks like. So in terms of notation, I'll sometimes refer to uniform expansion as UE, and the mu to the n is convolution n times. So again, just the nth step of my random walk. So an example of this, if I just take a random walk that is a point mass on two diffeomorphisms, say 1G and 1F, and it gives each of them half weight, to say something is uniformly expanding at step 1 is to say just this first quantity exactly. It really is just like two pieces of a computation. And to say it at step 2 is just slightly more complicated. Obviously, this gets worse and worse as you go on, but the basic idea is quite concrete. After n steps, you have grown. So let's do a quick example of what this actually looks like. So if I take a volume preserving diffeomorphism F, this thing will never be uniformly expanded. So if I put a point mass just on this is never uniformly expanding. And the reason for this is that volume preserving diffeomorphisms have to have Lyapunov exponents that sum to 0. So you'll always have a direction of shrink. You'll never have growth in the whole system. So somehow this is a property that in the volume preserving case, at least, can only exist if you have randomness, if you have more than one thing happening. But let's say we take 2. So let's do the example that I have written up. So say we have mu is point mass on 2. And let's say, in addition, that both of these have a hyperbolic fixed point x, the same hyperbolic fixed point. So So what ends up happening? Well, F will have an unstable and stable direction. So let's say these are, oh God, pretend that actually goes through the point. So let's say this is the stable. And this is the unstable. So again, this can never be uniformly expanding because we will always have the stable direction. It'll never grow. But let's say we add in G. And let's say this has this stable. And this has this unstable. So this will be uniformly expanding at this point, assuming the stables don't line up exactly. So the only way, well, there are actually two ways that this can be not uniformly expanding, that it won't meet this criteria at the point X for all vectors. The first one is if the stables line up exactly. And the second one is if the stables and unstables line up exactly and they happen to cancel each other out, right? So in the first case, what is actually happening is that we have a non-random direction. So somehow along the stables, if they collapse and the two stables are together, what that means is that we have a non-random direction of shrink, and it's preserved under the dynamics. Like it has to exist. And this is going to show up later. It turns out in a more general principle that the real obstruction to uniform expansion in most dynamical systems that we're going to care about here is a non-random structure of some kind. And this makes sense since somehow deterministic things can't really be uniformly expanding. Like they cause problems. All right. So because of the 0-1 law, everything that's not on the stable will get sucked into one of the unstables. So if they don't line up, we're good. Okay. So other properties. Well, in addition to being sort of extremely random and requiring randomness, this is a finite time condition. This ends up being very useful. You know, in dynamics, very often we're looking at limiting processes, and those things are hard to deal with, right? If I'm going to compute the Lyapunov exponents, I'm going to usually have a bad time. And being able to know things about the Lyapunov exponents or know things about my dynamical system in finite time is very useful. So it's a finite time condition. Was there a question? Okay. Finite time condition. It guarantees positive top Lyapunov exponent. Actually, it gives you a uniform lower bound on the top Lyapunov exponent for every stationary measure. So it's quite a strong condition. It's open, which means that in some sense for measures with close support, you will also have uniform expansion. So this lets you do really interesting things like if you construct a measure that's uniformly expanding, but has some properties you don't want, you can try to approximate it with measures that have properties you do want, and usually it'll work. So you can usually get uniform expansion in a pretty broad category of places. The last one, which is not the last one on the slide, but the last one I'm saying, is computer checkable in finite time. So this was shown by Brian Chung in 2020. And at first glance, it seems like it should work really well. Like to do this, all you have to do is check a finite number of points because the tangent bundle is compact and M is compact. So and this is a very nice continuous condition. So you can just pick a finite number of points, and a priori, you can just check it at those points, show it's uniformly expanding. In practice, it seems like this is going to be a very difficult thing to actually use to its full advantage. I feel like there should be uses here, especially because if you suspect a system is uniformly expanding after a certain number of steps, you might be able to just compute for that number of steps, and that could work out better. But as it stands, this is not as useful as it could be, or as maybe we'd want it to be. Yeah, so that's gonna, a priori, you have no idea. It would entirely depend on the dynamical system, because what's gonna end up happening is you need to have some idea about the norms of your dynamics. All right, so along the same lines, again, this is something that you can ignore if you're not familiar with Grassmannians. Otherwise, so it's not enough to talk about growth of vectors. In 2 dimensions it is, because we don't have any interesting subspaces. But in higher dimensions, we have to think about subspaces because you can very easily have a situation where you have something, a three-dimensional subspace that shrinks, but a two-dimensional subspace, but all two-dimensional subspaces grow. So this is a phenomenon that can happen. You can have uniform expansion sort of on the vectors, on the tangent space, but not on the second exterior power, or not on the two-dimensional subspaces. So because you can have this happen, we have to eliminate this this problem at all levels. So we consider all dimensions when we think about uniform expansion in the theorems that I'm going to talk about next. So if mu is uniformly expanding for all dimensions between 1 and d minus 1, then we call it uniformly expanding in all dimensions, which is pretty obvious. So the reason why we need this bigger definition is because a lot of the work that's happened in this with this definition in this area has been on surfaces for a while, and there have been recent things in higher dimensions. So this added definition is to let us use the same tools that worked very well in surfaces in higher dimensions. Yeah. Yes. Good question. Yeah, so when I say Grassmannian and norm of Grassmannian, I'm thinking of it as embedded into projective space of the exterior power, and then taking the norm of the exterior power. So essentially, I'm treating it like the unit tangent function. You can do it all without that, but you just have to have an extra term, so it's more right. Other questions? Okay. All right, so why do we care? Right, I've told you about an object. I've described it to you. I've described some of its properties, but why do we actually care about it? So the reason why we care about this one in particular is because there are some theorems that have quite strong results that are very connected to uniform expansion. So these are works by Aaron Brown, Alex Eskin, Simeon Filip, and Federico Rodriguez Hertz. They're in prep at the moment, over 200 pages last I heard. And so they give us very strong results. So the first one is stiffness. If mu is uniformly expanding in all dimensions, so this works for any dimensional manifold, then we know that any mu stationary measure is invariant. So the stuff I said about at the beginning, where we might not have an invariant measure, but we will have a stationary one, you can just forget it. If we have something that's uniformly expanding, all stationary measures are invariant. We can forget the technicalities of stationary measures. The second thing is if we have the same condition, but also know that all Lyapunov exponents for all stationary measures, or all invariant measures because they're the same, are non-zero, then everything is either volume or finitely supported. So this is a very Ratner-like theorem. And in fact, it is very, very Ratner-like. So there should be, for people familiar with Ratner's measure classification theorem, there should be intermediate cases in here. Those intermediate cases are deleted because uniform expansion can't have any invariant submanifolds. So the fact that uniform expansion sort of prevents like invariant structures means that you can't end up having any of the intermediate cases. So everything is either the whole manifold or points. So these are very useful results. They're very strong. In particular, obviously orbits are very interesting to us in dynamics. And in particular, this says that any orbit is either finite or dense, assuming the conditions of theorem. Okay. So this is why we care. We would like to be able to use this, and we would like to be able to conclude strong things about uniformly expanding random walks. But to actually be able to use this, we have to know, do these actually exist? How frequent are they, right? I've given you one very hand-wavy example at a single point. In general, it turns out to be very difficult to write down examples of these things. So you can appeal to homogeneous dynamics and say, if you pick toral automorphisms with Zariski dense support, then you can get uniform expansion. For the same reason as this works, you're eliminating invariant structures, so you can't have any problems essentially. But outside of those sort of very classical examples, it's very hard to cook this stuff up, especially in the smooth set. So how common are these? So this was first answered by Raphael Potry in 2021. He looked at the two torus, and he showed that for any open set in the diffeomorphisms of the two torus, volume preserving, there's a finitely supported measure that is uniformly expanding, and its support is entirely contained in that open set. So essentially, you can kind of get them wherever you want. You can build a uniformly expanding random walk wherever you want on any set you want. In particular, his construction of this actually based it around a particular diffeomorphism. So it's not only contained in the set U, it's somehow contained in a very close neighborhood of a very particular diffeomorphism. So it is very close to one diffeomorphism. Now, honestly, having it be close to one is not very useful because randomness buys us a lot, and trying to turn facts about randomness into deterministic facts often doesn't work. So as an example of this, Brian Chung in 2020 actually looked at perturbations of the standard map. So random perturbations of the standard map, and he showed that that thing is uniformly expanding. So that thing has to have positive top Lyapunov exponent, but you can't conclude anything about the Lyapunov exponents of the standard map from that perturbation, no matter how close you can get it. Somehow the randomness isn't quite enough to say things about very specific maps. But this is very useful. It tells us that these things are very common. So my work is expanding on this. So I built on the work of Potry and showed that you can actually do this for manifolds of any dimension and any manifold. And in addition to saying that you can build something that's uniformly expanding, in the higher dimensions, obviously, you have to think about expanding in any dimension because you have to deal with the intermediate cases of the subspaces. And then the last one, there's no finite support of mu invariant subset of M. This is letting us use the theorem of Brown, Eskin, Filip, and Rodriguez Hertz to say more concrete things about the orbits, right? If you can use this last statement and say that the Lyapunov exponents are non-zero, you can then say that all orbits are dense. So it's a very nice characterization and a nice thing to be able to say that you can build on any set if you can. All right, so now this is the answer. The answer is they're quite common. They're more common than I would expect, though, again, randomness gives us a lot. So in the last couple minutes, yes. Yeah, these are all volume preserved. Yeah, so G is just volume preserved. Other questions? Okay. Yeah. Yeah, so you don't know any of that a priori. So you know that it preserves volume, but it could have many other things. Oh, no. Other? Okay. All right, so that's the result. So very briefly, the strategy of the proof. So for the sake of time, I'm not going to go into too much detail about these steps, but I'm going to focus on step 2 and give you a flavor of the others. So step 1 is show that if you're not uniformly expanding, it implies there's an invariant structure of some kind. Again, this is what I've been saying with the somehow you have to have randomness to have uniform expansion. Step 2 is you then construct something that can't have any of these invariant structures. And then step 3 is approximate with finitely supported measures. And because uniform expansion is an open condition, this last step can actually work. Otherwise, you'd have no hope. So something to note here, structure means proper measurable subbundle or conformal structure. So in general, this can be a very complicated thing, especially because you will often deal with, again, this is usually on the Grassmannian, but for the purposes of this talk, it's sufficient to think about it as you have a non-random direction, right? Somehow there's a non-random direction in your dynamics that is causing problems for expansion. So to briefly talk about step 1 involves, it's the only one of these that actually uses volume preserving. It is the key thing for volume preserving. And in step 1, you use a invariance principle of Le Drapier that was expanded by Avila-Viana to the smooth setting. And you use a pretty straightforward hop argument. And obviously there are some more technical details, but that's the core of that. Step 2, we'll talk about in just a second. And step 3 is, again, pretty straightforward. You just construct measures that approximate your continuously supported measure. And because it's continuously supported, it's not too bad to do. So we're going to go into step 2. All right, so step 2. The idea is that we want to use so much stuff that no structure can stay. So we want local transitivity. Essentially, I want to be able to move up in the fiber of my Grassmannian bundle or between, I want to move from any subspace to any other subspace. And I also want to be able to move locally on the manifold as well. The goal is like transitivity in the whole bundle at a local scale. And then you take that and you spread it across the whole manifold. And this lets you say that if there's an invariant structure anywhere on your manifold, then you can wipe it out with some positive set of these maps that you construct. So this is the goal. So pretend everything's in R2 for the moment. What we do is we cover our manifold, pretend the manifold is covered. We cover the manifold with a finite subcover of charts. And each of these we require some things I'm not telling you, but the key one here is that we map the big outer ball to a ball of radius r, and we map the inner ball to a ball of radius 1. And the reason why we do this is because what we're going to do on the ball of radius 1 is build this transitivity that we want, and then we're going to use the bigger ball to smooth everything out and make it volume preserving. So this is the goal. Okay. So again, we're replicating affine transformations. Well, I didn't say that yet. We are replicating affine transformations. So if we take a matrix in SL3R, again, pretend SL2R, and we take a vector, this thing will let us move transitively in between subspaces and on points between points on the manifold. So the R2 component will let us move on the manifold, and the matrix will let us move through subspaces. So this thing is what we want to replicate in our manifold. Now, of course, the problem is if I put this, if I put AX plus B on any point in my ball and I move it, I'm not going to get a map of BRA. So I have to take this thing that I've moved through space and sort of move the rest of the mass of the ball back into place in a nice, smooth way without harming any of the properties that I want. So what we do is we construct maps that go from the ball of radius r to the ball of radius r, and we require that they're smooth, and we require that on the inner ball, they are exactly the affine transformation. So they're just AX plus B, which gets us all the transitivity we could possibly need. On the boundary of the outer ball, they're the identity. So this says that they smoothly interpolate to the identity, and outside that, they'll do nothing. So this kind of lets us constrict to a particular chart. Each of these maps will be pulled back by a chart, and on each chart, we have as much movement as we want, essentially. And then, of course, we require that they're volume preserving. So the way that you do this is by constructing a flow that has AX plus B as the time one step of its map, the time one map. And then you use the fact that we're on a ball, and you use the Poincare lemma to sort of pull everything back, compose with a bump function to smoothly interpolate to the identity on the outside on the boundary of the ball, and retain the affine transformation on the inside on B1. So this idea is just, again, we're just smoothing the mass out across this ball. And then we build our measure mu to be supported on all possible charts. So let me actually break down what the measure is. So what we end up doing is say that, what did I do with this? B. So let's say GA. Right. So call GIA our maps. So this is the map on the ith chart that is doing the 8th affine transformation. And again, just a reminder that A is just a matrix and a linear transformation. And then what we do to construct our measure is we take some F that's in our set U, and we construct mu to just be, I'm just going to put a C. We put a point mass on F. This is to get us into the ball. And then everything else, we take a sum and we integrate, the sum is over I, and we integrate over a point mass on G A I composed with F. So this is Lebesgue on the ball. And then C is chosen so that this thing is actually a probability measure. So up to some normalization, we've picked something that has mostly continuous support, not quite, but mostly. And there's a huge open set of diffeomorphisms or volume preserving diffeomorphisms on our manifold that will take anything and move it to a different place. So there's like, it doesn't matter what point you pick in your Grassmannian, you can pick many maps that will move it away from itself. So this lets us break structure with a set of positive measures. And this is the core goal. Okay. So a corollary to all of this. So this is the meat of step 2. A corollary to all of this is using my work and the work of Alex and Simeon and Aaron Brown and Federico Rodriguez Hertz. If D is 2, you can conclude that for this particular measure, volume is the only stationary measure and all orbits are dense. So again, this is a very useful thing to be able to say. It lets you say that on any open set, you can construct such a. And again, this is also a finitely supported measure. And I hope to prove this for D greater than 2 in future work. It is much more difficult, of course, because as soon as you move off a surface, you no longer have positive all your Lyapunov exponents non-zero. So on a surface, if your top one's positive, you're good. In higher dimensions, you have a lot more problems. So higher dimensions is still open for this. Okay, and that's it.
You mentioned that you work in the volume preserving setting, but
Yeah.
I didn't understood if the same technique will work if you just pick an open set of dissipative diffeomorphism.
So it won't actually. And the reason why it won't is because you need to have, so the reason why volume preserving is special in this case is if you have the top exponent 0, all of them are 0. And this fact lets you use the invariance principle of La Drapier and Avila-Viana. And without that, you really don't have any hope to show that such an invariant structure has to exist. So in the non-volume preserving case, you could absolutely have no uniform expansion and no invariant structure. So you'd need an entirely different method.
But the result of Pottery is not specialized to the volume preserving setting, or is
I think it is, yes.
It is. Okay.
Other questions?